one of my favorite topics. Stress, strain, and Young's modulus. You'll see it in GCSE, A-level, engineering, everywhere really. Stress. We'll start off with stress, and we all get stressed. So do materials. And all stress is, we'll do two types today. We'll do two types, because there's more than two, but we'll do two. If I get a bit of metal, or a bit of wood, or a bit of plastic, we're going to do two types today. If I put a force there like that, that force is going to cause a stress. That force is going to cause a tensile stress. If you pull anything, you're going to get a tensile stress. It's called tension. In tension. It's going to make it longer. Stretch it. Tensile stress. That's one stress we'll do today. Force pulling something. And the other one is going the other way. There's my whatever it is. That's going that way. There's the force going that way. This one now is compressive. It's a compressive stress. Nice yellow, that, isn't it? Compressive stress. It's being squashed. It's being squashed. One's making it longer, stretching it. Tensions are getting longer and compressions are getting shorter, squashing it. We're only going to deal with one direction. Obviously, when you pull something like that, it's going to get longer and thinner. But we're going to just go with the longer bit. When you squash something, purely squashing it, you're going to get it shorter and fatter. But we won't go that far today. So the formula for stress, because there's always a formula. So stress for us is force divided by area. You should all know what a force is. You should all know what area is. That's our stress. Keep it simple for now. Force is measured in newtons and area is measured in meters squared. Might be different here in America. So the unit of stress, there's a few, is newtons per meter squared. It can also be called, I'm going to call it a Pascal, PA for Pascal. You might also see it, depending where you are, well, you'll see it over here anyway in UK. PSI, pounds per square inch. Okay, if you're in America, pounds per square inch. And you might also see stress, pressure as bar. So you'll see all of them. We're going to be using Pascal, my favorite unit. Okay, but you might also see in PSI on your bike, pressure in your tires, stress in your tires, bar in your pressure in your weather forecast. But we're going to be using stress force divided by area. First one is going to be a metal bar in tension. So here's my square metal bar. I did A-level art, look. There's my square metal bar. Let's pretend it's 100 mil. A different pen. It's 100 mil square. 100 mil. Not to scale, before anybody has a go at me. Not to scale. It's 100 mil by 100 mil. We've got to be in meters, by the way. So 100 millimeters is the same as 0.1 of a meter. There's 1,000 millimeters in a meter. So all you've got to do is divide that by that to get it into meters. We've got to be in meters. Let's pretend we've got a force pulling it. Let's say we've got 30 kilonewtons. 30 kilonewtons pulling this thing up. Okay, that's my force. What is the stress on this object? I don't know, Mr. Bond, but we'll find out. Because I know stress is force divided by area. It's square. So the force is 30 kilonewtons. That is 30,000. 1, 2, 3. Or on your calculator, you could do 30 times 10 to the 3. Divided by the area. The area it's square. It's that cross-sectional area by there. And that's a square. 100 mil by 100 mil. The area of a square is that times that. So the area of this thing is 0.1 times by 0.1. Bit of maths, bit of maths, bit of maths. Use a calculator. So it's force divided by area. Don't forget the kilonewton. So I'm going to go on here, look. 30,000 divided by 0.1 times by 0.1. You might be able to do it in your head. Press, right? Get a load of numbers. Get a load of numbers. 3 and loads of noughts. We've got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's how many pascals that is. Or if you want to go newtons per square meter. Okay. I'm going to press E and G on my calculator. It doesn't mean English. It means engineering. I'm going to move this decimal place. 1, 2, 3, 4, 5, 6. So that is the same as 3. Look. If you can see it. 3 times 10 to the 6 Pascal. Also known as 3 megapascals. That's how much stress is on that thing. Stress is force divided by area. That's in tension. Easy peasy. No stress there. We'll do another one now, but we're going to go the other way. We're going to go the other way. I'm going to go now. We go compressive. Compression. Squashing it. Compressive. Because you can't have tension without compression. We'll do a round bar this time. So it's a solid round bar. There's the clue. It's round. It's round. And let's pretend it's being squashed. There's my yellow. It's been squashed by, let's say, 40 kilonewtons, 40,000 newtons. The diameter of this thing, the diameter, it's round, right? So it's that area there. The diameter of this round bar is 70 millimeters. You might see this as a symbol for diameter if you're doing engineering. Okay. Diameter. So we're going to be doing stress. What is the stress on this object? Well, the stress is the same formula as last time. Force divided by area. We know the force is 40,000. Look. The area this time is a circle. It's a round bar. So the area of a circle you might know is this, pi r squared. R is the radius. That's one way of doing area. I like to do this. There's another formula, pi d squared over 4. Most people probably use this. So we'll use that. You've got to make sure, though, that you divide your diameter by 2. Because some people miss that. Because radius is half diameter in it. So diameter is 70, which means the radius is going to be 35 millimeters. Which in meters is 0.035. It's got to be in it. 35 divided by 1,000. 1,000 millimeters in the meter. Or on your calculator, you could just do this. 35 times 10 to the minus 3. Milli in it. Milli. Use that button. Look. Button there. So stress is force divided by area. We know what the force is. The force is 40,000. Don't forget the 1,000 times 10 to the 3. 40 times 10 to the 3. Look, that button there. Or do 40,000. The area is pi r squared. So pi times the radius squared, which is that thing there. 0.035 squared. Don't forget the square. Let's see what happens. Let's go there. 40 times 10 to the 3. We'll divide that by pi, shift pi times by 0.035. Don't forget the squared. Pi r squared equals all of them numbers. You get all of this number here, look, on your calculator. 10393792.2 Pascal. Press the E and G button. Press the E and G. Engineering format. Saves writing all of that down. It's going to move it 6 times. Bang. 1, 2, 3, 4, 5, 6. So you could write this 10.39 times 10 to the 6 Pascal, also known as 10.39 megapascal. Because 10 to the 6 is megabyte. If you want to, I suppose you could go 10.4 megapascal. Compressive. That's how much stress is on that thing. Amazing, isn't it? Stress. Force divided by area. Got to be in newtons, got to be in meters. The next part of this, because while we're here, we might as well do it all. I'll have some more squash. The next part is right there. Strain. Because a force creates, I'll write it down here. Strain. When you strain, things change, right? When you apply a force will give you a stress, which I suppose gives you a strain. And all strain is, I'll draw something else, look. If I've got something like that, and if I'm pulling it up like this, it's going to go, it's going to change in length. I'm going to label this L. L is original length. And this bit by here, how much it's been squashed or pulled up, is the change in length. That's all strain is. Use a strain gauge normally. So obviously we go the other way as well. If I was squashing it, I'd have a change in length going that way. Okay. For now, we're just going to be going in one direction, right? We can use a thing called Poisson's ratio, but we won't do that today. So the formula for strain, get a pen. Strain, how much strain we're under, is change in length. Delta L means change. Delta, that's triangle thing, means changing something over length. So that means change. That's the change. And this is original. That's all it is. That's the formula. So we can work out change in length or we can find strains. It's up to us. Okay. I'm going to go back now and I'm going to work out the strain. This one by here, look. This one here. We go back to this one. 100, 3 megapascals, right? So this one, let's work out the strain on this thing. Here's my square object again. There's my square thing. Let's pretend, so remember we had 30 coming up. 30 kilonewtons coming up. Let's pretend this thing was 2 meters long and that force, that tensile force is stretching it by, I don't know, 3 mil. 3 millimeters by there. It's getting longer by 3 mil. So the delta L, the change is 3 millimeters. It's changing by 3. Obviously, if it's getting longer, it's getting thinner, but we're not worried about that yet. So we need to find the strain. What is the strain? I don't know, Batman. But I do know the formula is that. Strain, it's a ratio, right? So you've got to have length over length. There's no units for strain. Get a pen, go on more. So what's the strain on this object? Well, the strain is going to be the change in length. Right, this needs to be in meters. We'll keep it in meters. The length is 2. This now is going to be 0.003 in it. 3 millimeters in a meter. You could also write on a calculator if you want to do this. 3 times 10 to the minus 3. Same thing. Milli in it. Milli. You could write 3 times 10 to the minus 3. It's a length over length, so we've got to be in the same unit. We'll keep it in meters, but you could be in millimeters or miles, as long as you're the same unit. So the change is 0.00. A change will do you good, right? So 0.03, well, there's a 15 somewhere in there. So that divided by that, I'm going to go 0.003 divided by 2 gives me that, look. 1.5 times 10 to the minus 3 on your calculator. That's how much strain. There's no units. This is a ratio. No units. If you don't like that number, it's the same as this 0.015, isn't it? 1, 2, 3. That's the strain on that thing. Normally a strain gauge will do that for you. Oh, I'm losing stuff here. Okay, we'll do the same thing for the other one, just for a bit of laugh. Where was it? This one here is compressive. Where are we? For now, it's the same thing. You know, compressive and tension always is different direction, but for us, we'll just use the same. This one here, look, while we're there. So this one's the round one, different color. So there's the round one. Let's pretend it's at 40 kilonewtons by there. Let's pretend this one is 3,000 millimeters. That's 3 meters, really, isn't it? It's been squashed, look. It's being squashed. So let's pretend, like a can crusher, it's been squashed by 5 millimeters. Okay, it's getting fatter and fatter and wider in it, but we're only going to deal with the 5. Right? What is the strain on this object? Strain is change in length. Delta L means change over length. Okay, as long as we're in the same units, doesn't matter what we're doing for strain. So I got millimeters there and I got millimeters there. I'm going to keep it in the same units. Saves trying to muck about. So the change in length in millimeters was 5, not a lot. Divide by the length in millimeters, which is 3,000. You could convert to meters and get the same answer. 5 divided by 3,000 quickly, was it 600? That, let's see what that is, 1.6. It's Sunday, isn't it? 5 divided by, no, come on, Mug. 5 divided by 3,000. Bang. 1 over 600, let's press E and G. 1.67, if you want it like that. 1.67, something like that, times 10 to the minus 3. That's the strain on that object, no units. You can use that. Normally you would use a strain gauge to find the change in length, but we're going the other way. That's the strain. So we've done stress and strain. Very common in engineering. You'll do it in A-levels, GCSE, engineering, H&Cs, blah, 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 blah. More squash. While we're there, we'll do one more thing. I'm going to do now a thing called Young's modulus. Young's modulus. You might have done Hooke's law. Young's modulus is really, I'm going to use the word stretchy, but I don't like using the word stretchy. Don't use the word stretchy, but it's how stretchy something is. The higher the Young's modulus, the less stretchy it is. Like diamond has got a high Young's modulus. Diamond. Plastic, whatever plastic is, has got a low Young's modulus. You might have seen a graph like this in physics or chemistry or something, or materials. This tensile test graph, you might have seen that. You might have, because you might have done Hooke's law or something like that. Okay, Young's modulus is how stretchy something is. Diamond is not very stretchy. It's got a high Young's modulus. Plastic has got a very low Young's modulus because plastic is stretchy. Stretchy. Anyway, I'm blabbing on. Young's modulus, there's a formula, and all it is this. How stretchy something is, Young's modulus, and all it is stress divided by strain. Get away. That's why we're doing stress over strain. That's all it is. So something with a high Young's modulus is not very stretchy. Something with a low Young's modulus is stretchy. So what we'll do now is we'll go back and we'll work out the Young's modulus of these two bits here if they were bits of metal. So we'll do, where are we? Come on. We'll do this one here, look. We'll do that one first and we'll do this one. So the stress on this one was 10.4. I'll do it here, look. So the stress is 10.4 megapascals, right, on the round one. That one there, look. That one there. And the strain on the round one was 1.67 times 10 to the minus 3. So the strain was 1.67 times 10 to the minus 3. What is the Young's modulus? E is Young's modulus. It's stress divided by strain. We're doing a bit of materials now, see? So all you've got to do is do the stress divided by the strain. Make sure you do the 10 to the 6. 10.4 times 10 to the 6 divided by 1.67 times 10 to the minus 3. Don't forget the 6 and the minus 3. The bigger this number is, the less stretchy it is. Right, here we go. 10.4 times 10 to the 6, look. We'll divide that by 1.67, rounding up to the minus 3. That's what you get. Equals all of them numbers. Oh, I'm not going to write the numbers down because there's loads of them. I'm going to press E and G, and it gives me 6.2. 6.22, perhaps 3, perhaps. Leave it like that for now. Times 10 to the 9 Pascal. 10 to the 9 is giga, so this is going to be 6.22 gigapascals. So that will tell you how stretchy something is, if you knew what that meant. Okay, in comparison, metal is like 200. Right? So that's the Young's modulus for this thing. Let's work out now the other one to see which one would be stretchiest if we knew the material. So the other one, the square one, I'll go back. Bear with me. The square one was 3. Square one was 3 megapascals of stress. And the strain was 0.0015. 0.0015 strain. Stress divided by strain, everyone's a winner. So what was the Young's modulus? Well, E is Young's modulus. It's stress divided by strain. In the calculator, do it before me if you want to. Stress divided by strain, 3 megapascals, 3 times 10 to the 6, divided by 0.0015. The 2 somewhere in there. Let's see what that is. 3, 10 to the 6, don't forget 10 to the 6. We'll divide that by all of that, 0.0015. Bang. All of them noughts, look. 2 and loads of noughts. I'm going to press E and G. Save the ink. 2 times 10 to the 9. 2 times 10 to the 9. Pascal. The unit of Young's modulus is Pascal. That is 2 gigapascals. Isn't that amazing? Obviously, all these values you can find in books and stuff, can you? So the higher the Young's modulus, the less stretchy this thing is, whatever it's made out of. That's 2. This one was 6.2. That there is not as stretchy as that. That 2 gigapascals means whatever this thing was made out of is a bit stretchier than that. Okay, Young's modulus is how stretchy something is. Stress, strain, Young's modulus, you'll find it everywhere. I'm going to go now. Don't forget to follow me, etc., etc., etc. I'll do some more lives in the week. See you later on. Any questions, let me know. I'm going to press stop now. I'm going to squash. Over and out.